we have already seen this sequence of stochastic processes yk, which are like precurred iterations, and then we have shown that this yk, this sequence is Cauchy in the L2 space with respect to the product measure, and then that limit of this we denote by x, and then this x is the candidate process which we need to show that okay, this solves the stochastic differential equation. It is not quite right to say that okay, we are going to prove that x itself solves that equation, but okay, from x we are going to find out another okay, which is very close to x, okay, a modification. So that would be this. Okay, so here we recall that this iterations yn plus 1 is defined using yn here for all t. Now we consider this right hand side. So the right hand side, if you vary t, so this is also a process. Okay, for every n we get a stochastic process here, for every n we get a stochastic process here, and the new goal is to show that this stochastic process 0 to dot means the t, but t is running, okay, so generic t, bs yns ds converges to bs xs ds. Which x? This x. Okay, so that is the goal we have. Our goal is that showing that okay, this converges to this part, this converges to this part, and this anyway converges to in this L2 norm of the product measure in an appropriate manner. We need to show this. Okay, so first thing we do in the next slide. So here, before doing this, let me emphasize the plan here. The plan is that x is the limit, and then yn is anyway this thing, and then if we would be able to prove, if we prove these two things, we would be able to prove that this limit would be this, okay, and then that means x is same as this almost everywhere with respect to this measure lambda cross p. But that is not quite same as the statement, but very close to the statement, and with this we are going to find out the final solution. Okay, so that is the plan. So we now go to the first claim, the claim number 1. So this bs yks ds minus bs xs ds, so this difference I need to show goes to 0 with respect to this norm L2 norm of lambda cross p. Okay, so what we do is that we write down the meaning of this. If the meaning is 0 to t integration, expectation inside or outside is okay because it is non-negative term, is it only we can do. And then here mod of 0 to t, so at t time whatever is value is bs yks minus bs xs ds 0 to t, okay, that is its value. But then with this t also you need to integrate because it is lambda is corresponding to the measure on the time domain, p is measure on the omega domain, okay. So for that we are getting expectation. Now here we are using Hölder's continuity for inside thing, okay, expectation of so here square of the integration, okay. So here what we are doing is that we are going to get that is less than or equals to t times that integration of the square, okay. So that we are going to get, anyway this is like a vector, so we're going to normal square. So here now this thing, okay, we can again upper bound by small t, you can replace by capital T, and here small t can be replaced by capital T because anyway the integrand is non-negative. So we can have this upper bound, and here norm of this is like using the Lipschitz property of the function b with the second variable, we get this less than or equals to d square times this variable yks minus xs whole square. So we are using that Lipschitz property of b here. So here we have integration is running from 0 to t, but here outside the whole inside is not independent of small t. So this t d square etc comes, and with respect to this capital T another time comes. So I would get capital T square, so capital T d whole square, and then this thing we need to identify. Right? What is this? That expectation of 0 to capital T of this there is a stochastic process square and ds. That is nothing but the L2 norm with respect to the product measure lambda cross p. So this inside part, okay, is this thing, but we have already shown that yk converges to x in this norm, so this part goes to 0, or in other words that this converges to 0. Okay, so here the first claim is proved. Now we go to the second claim. Second claim that involves that integration with respect to the Brownian motion. So next we use the Ito's isometry for this regard. So again 0 to dot, okay, 0 to dot. So these two processes we want to write down, then the square of the L2 lambda cross P norm. Here we use that the definition of this norm, that is integration 0 to capital T, expectation of 0 to small t, okay, at a t value, whatever its value is, that is this thing, okay, sigma square is square. And here we have also used that Ito's isometry. So everything together, actually here I have jumped some steps, okay. I mean this whole square was there, and then the integrand square times ds because of Ito's isometry, and then dt. Okay, so basically I have used two things here, the definition of the norm and then Ito's isometry. Okay, so after getting this, we do as we have done earlier, that we use the Lipschitz continuity property of sigma with respect to the second variable here. So again we are going to get d here, since square is there, so I will get d square, and then yk minus x whole square, okay. And then this small t I can upper bound by capital T here also, okay. So here this integration of outside integration would be capital T, so I would get capital T from the outside integration, because inside would be independent of small t, because I have replaced small t by capital T here. Now I identify this term, expectation of integration of the process square and ds. What is this? Again the norm, L2 norm under the product measure. So that is yk minus x norms. Here actually I should have written square, so square is missing. Earlier also, here also I made the same mistake. Here I should have written square here, okay. So square, so that goes to 0, that goes to 0, so the whole thing goes to 0, okay. So what we have obtained is that in that iteration term, right hand side, those two integrals converges to the integral with respect to x process, okay. So hence yk converges to x, which solves the SD for every t omega from this, except possibly for some zero measure set. So lambda cross p in 0. Why is it so? Because both sides, because this side converges to the integration with respect to x, these things, this side also converges to x in the same norm. So both are, and both are actually same sequences, so same because they are equal. So a sequence converges to do different functions, okay, in the same space, okay. So then they should be in the same equivalence class. That means the left hand side is same as right hand side almost everywhere. Okay, so what did we get then? We got that x satisfies that SD for almost every t and omega, okay. So that means it might not satisfy the SD for some combination of t omega, that set I am writing as capital N. However, the measure of the capital N will be 0. Is it clear? The measure of that will be 0, okay. So here, by arriving at it, we are not yet done with the proof of the theorem, because there it says that for each and every t it should be true, okay. So we need to do a little more work here. So here we introduce some notation. So given n, that for that n, this notation n restricted t, so we call the t section, okay. N this restricted t, we denote this notation to denote the set t section. What is t section? That set of all omegas, small omegas, such that t comma omega belongs to capital N, okay. Now since n is a zero measure set, I cannot just say that, okay, this would also be a zero measure set, that for a particular t section, okay, that set may not be a zero measure set. However, that measure would be non-zero, okay, only for zero measure t's basically. So I would write to say that, okay, the measure of t such that the probability that n restricted t is not equal to 0, that is equal to 0. Why can you do that? Because if it is not the case, then n would have a positive measure. Imagine that if it is not 0 positive, that means you got some positive measure of set of t on which the t section of n is positive measure. So you'd be able to get one nice subset of n which would have positive measure, but n has 0 measure. So we have this, okay. So now we define. So why are we doing all this? Because we need to show that xt solves that SD for each and every t, but we are not yet there. So that's why we are classifying these two parts, okay. So now we consider those t's, those time points t's, such that the t section of n is 0. So that is most of the cases. There I am writing x tilde as x. So x tilde is a new process which is same as x. So most of the cases x tilde is like x. But when the t section is non-zero, okay, then I take x tilde as this x0 plus integration 0 to t bs xs ds plus 0 to t sigma s xs dws. Why are we doing that? Because the good thing is that x is already defined, all different things. So then I take this, okay. And then our goal was to show that x tilde solves that SD. Now, even for some earlier point s, x tilde was different from xt, okay, still I can replace here x by x tilde, because the time points where x was different from x tilde, that was 0 measure set. So there I can therefore change this. So I would get x tilde is also solving like the x tilde here, okay. So I would be able to get that, okay. So that is the idea. And we would put x tilde 0 is equal to x0 if that is not coming naturally, okay. So if required, we would also put that, okay. So now we say, okay, since we know this, so then for each and every t positive, okay, so this is the thing what I have already explained, that we can write down x tilde t is equal to x tilde 0 plus integration 0 to t b s x tilde s ds plus 0 to t sigma s x tilde s dws. So I would be able to get it for almost every omega. Why? Because here we started with, say, we have fixed one omega, and then we have started with t, and then we have checked that whenever this is the case, we have put these xt values and then these values. So what we have obtained, this x tilde t, it actually satisfies, I can replace x by x tilde here. By doing that, it might not agree with this only at time points on finite on 0 measure sets, but however that integration would be the same, because it is integration with two Lebesgue measure here and the Brown motion here, okay. So that is the thing we obtained here. Now this is just a candidate, okay. So we have many things to do now. First thing is that we need to show that this is continuous solution, okay. So the t to x tilde is continuous, and here what we have obtained is that for each t this is true with probability 1, but we need something stronger. We need that this is true for all t and probability of that is 1. Okay, basically we need to prove that probability that x tilde satisfies the SD for all t, okay, the process, and probability of that is 1. So that is the thing we need to prove, okay. So it is like a modification kind of thing, but we need kind of indistinguishability, okay. So what we do is that we note that the expectation of integration 0 to capital T sigma s x tilde s whole square, a quadriviation of Brownian motion, that is ds actually. So I am writing this way. So is less than or equal to, so here we are using the at most linear growth property of sigma. So then I would get 1 plus mod x whole square, but then I would write down 2, I'd like to take square inside, so I'll get 2 here. So I'll get 2 times c square expectation of 0 to capital T 1 plus mod x tilde square ds. And then this part we recognize that this is nothing but again this L2 norm of this x tilde 1 plus x tilde, but 1 I would take outside, so I would get t here. So 2 times c square times capital T plus this thing. However, x tilde is in this space, so this norm is finite, so we get finite thing. So why are you doing that? Because we do this to use the theorem what we have done earlier, that if a stochastic process is such that, I mean, this whole thing is finite, then this is in the class of L star or W, okay, of this measure, and then this integration of sigma with respect to the martingale W would be a square rectangle continuous martingale, okay. So since this is finite, so we are using the theorem what we have already visited in second week or maybe, yeah. So when we have introduced a stochastic integration, so using that we know that this process is in L star W, but W is, the quadrification of W is dt time itself, which is absolutely continuous with Lebesgue measure continuous function, and therefore L star of omega is same as L of omega, and from there we know that integration, so it is a very short notation. Actually, basically I want to write down the integration of this thing with respect to dWt, okay, that stochastic process 0 to t would be a square integral continuous martingale. So what we have done is that t to this map is continuous almost everywhere. So this map is continuous, okay, almost surely. Now we consider this omega star. Omega star is basically, I mean, one probability one measure set, and for all omega in omega star, so this is continuous. So we are actually picking up those omega for which is continuous, because here we have obtained almost sure continuity, correct? So omega star is the space of events, the set of events for which this is continuous. Now what we do is that we take C prime of omega, which is supremum of this quantity, that 0 to t is sigma s w tilde s dws, this quantity. This continuous function on a compact set, so this supremum is finite. So we would get that C prime would be finite for every omega from omega star. So C prime would be finite with probability 1. Okay, so whenever omega is coming from omega star, I would get C prime some finite number. That need not be bounded. Okay, C prime need to be a bounded random variable, but it is finite random variable. Okay, that much we can say. Okay, so now we talk about what is X tilde. So here we are using this equation. Okay, so this star. So we use this, right, because we are going to use this equation time and again. So we are giving a name just double star. So there we use triangular inequality. So a norm of x tilde t less than or equals to x tilde 0 plus 0 to t this thing plus C prime. Okay, why? Because this whole thing is less than or equals to C prime. And then this together, the C prime and norm x tilde 0, and from here again using the Atmos linear growth of B, I would get, okay, this is less than or equals to some 1 plus something, and then I would get some constant Ct, everything together I would write the C double prime. So this whole thing is less than or equals to C double prime plus C times of integration 0 to t norm of x tilde as ds. Okay. So here same x tilde appears both sides. Here we have t, here we have s0 t ds. Okay, we got this inequality. So this is dictating us that, okay, this is the place where we can use Gronow's inequality here. This is true for all t in 0 to capital T. Okay, so earlier if I would not have taken x tilde but x, I could not have said that, correct? Because it was the equation was true only almost everywhere, correct? But here we know that this double star is true for all t, so that's why you can write down this. So now we can use Gronow's inequality, so to say that, okay, this x tilde is less than or equals to C double prime e to the power of Ct. Okay, so this C and this C double prime e to the power of Ct. Okay, so this is true for all t in 0 to capital T is finite. So this supremum over all these things is finite. Okay, that we are getting almost surely. So like in omega star, whenever omega in omega star, we are getting this. Okay, so we are getting this is finite. So now for all omega in omega minus set minus n, okay, so this n is I mean different from the earlier n basically. So I should have written omega in omega star here. So x tilde t is less than or equals to C double prime omega e to the C. There is a typo C capital. So this line there are many typos actually. Okay, so whatever is written here, I'm just writing this again. So okay, so thus Now we consider S to be S X tilde as this map. Okay, so what can I say about this map now? Because X tilde turns out to be finite since it is bounded. Okay, it turns out to be bounded. Okay, for almost every omega. So for almost every omega it is bounded, and B has at most linear growth property. So this map on 0 to capital T would be bounded map. Okay, is bounded with probability 1. Okay, so here also there is one typo, integration 0 to T. This should be integration 0 to capital T, T to that map. Okay, so since it is then bounded integrand on this in interval, so then T to integration 0 to T, this as a function of T, this is continuous. So we get continuity of this on this interval 0 to capital T with probability 1. Okay, so here we look into this double star equation. Here that means we have obtained that it is continuous with respect to T. Here continuous here. So right hand side is continuous function of T. So left hand side is also continuous function of T. Okay, so we proved that X tilde is continuous in T. Okay, so this is proved. But now we have to prove this. Okay, so now here what we do is that, so here whatever I told here, it is written that right hand side of double star is continuous, so left hand side, which is X tilde, is continuous. Now we consider the time points T, which is rational number in 0 to capital T, in that closed set, all rational numbers. So this set is countable set. Okay, this is a countable set. So for each such set point T, I know that double star is true. So double star is true for almost this thing, okay, with probability 1. That means with some small set, okay, zero measure set, apart from that zero measure set for that particular T which is coming from this countable set, okay, this equation is, this double star is true. We call that AT. So AT is that zero measure set, okay, for a particular T which belongs to here, such that in the complement of AT, okay, that equation would be true. Okay, so the AT is the space of fields. Now union of all AT is 0 because countable union of zero measure set is 0. Okay, so what we can do is now that we can write down that the double star follows. Okay, for all T in this set, the event of this event has probability 1. So probability of the event that double star, what is double star? The probability of the event that this equation is true for all T rationals in 0 to capital T, that is 1. Okay, now if that is the case, then we use that Xt is continuous. Since this is continuous, on both sides are continuous, so both sides are matching. So the left hand side and right hand side are matching on a dense subset, on countable many. So the rational number is dense in R. So left hand side and right hand side are matching on a dense subset, and both left and right hand side as a function of T are continuous functions. So they must match on the whole interval 0 to capital T. Okay. So using the continuity of X tilde, we achieve that X is the solution. Okay, like the X tilde satisfies SD for all T is equal to 1. Clear? Okay, thank you very much.